So the practice set that's posted on Google Classroom, you guys should all have that open. That's what we're going to be working on today. And there's a link to this simulation that's there. So the simulation looks like this, and what it'll tell you is we're going to set up the experiment with copper on the left side. So we're going to drag this to where it says copper. And then on the right side, we're going to pick our other electrode, which is going to be magnesium. Okay. So this is going to be our galvanic cell setup. This is hooked up to a voltmeter, which is right here. Right now it's turned off, so we don't see what the voltage is running through it. And we learned yesterday that to have a thermodynamically favored cell, meaning one that is going to have electrons flowing through it, we want to make sure that we have an E cell that is going to be positive, okay? So what we're going to do is we'll set this on, okay? And this is telling us the voltage that's flowing through. Now at the bottom it says see molecular scale, and what it's going to do is show you what's happening at each part. I should have played our song to begin with, but remember that it talks about electrons. We start at the anode, electrons are lost there. They flow through the wire and then through the load on fire, which is our voltmeter. They enter the cathode and they reduce the cations, and the anions flow through the salt bridge back to where? The anode, okay? So this is how it's going to be flowing through. So what we're going to do is we have the half reactions for magnesium reduction and for copper reduction at the bottom, okay? And so we can actually write the thermodynamically favored balanced equation. We can calculate the voltage for the cell. We can do all of these things, as well as we're going to take this diagram and actually label what it says, okay? This makes it annoying to have to flip back and forth between, but we'll make it happen. So I'm going to go back to my dot camera. Okay. So using our voltaic cell, first thing we're going to do is we're going to come down here, we're going to answer these questions, and then we're going to take this diagram and we're going to label all of the things, okay? So the first thing that we need to do, it says write a thermodynamically favored balanced chemical equation for the overall reaction. So remember, to make a reaction thermodynamically favored, the overall voltage for the cell, or E cell, has to be positive, okay? So both of these are reduction half cells. We can see we have a reduction here, adding 2 electrons to give magnesium solid, right, going from 2+ to 0. Oxidation state for copper, 2+ to 0. And then we have the voltages for each of these reductions. So if we want this E cell to have an overall value of positive, which of these 2 reactions are we going to have to flip? Connor, which reaction? The magnesium or the copper are we going to have to flip so that this is thermodynamically favored?
The magnesium, because it needs to be positive.
Yep, magnesium because it needs to be positive. So what we're going to do is we're going to go ahead and flip this guy around. And when we flip it around, we would end up with magnesium solid making magnesium 2+ plus 2 electrons. And that means the voltage of this flip cell is now positive 237. Okay, so it says write the thermodynamically favored balanced overall reaction. Okay, so what we would have then is magnesium solid plus copper 2+. And because we have 2 electrons in each, right, on opposite sides, the electrons will cancel out. So then that's going to make, on the other side, what would our products be? Ami, what would we have for products?
M. 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 + 2 +
MgCu.
So you get Mg 2 plus aqueous plus Cu solid. Okay, so that would be my overall reaction. It's just calculate the overall voltage for the cell. So Olivia, how would I get the overall voltage for the cell?
Add the two together?
Yeah, we'd add the two together. So now that we flip this around, we're going to take the voltage from the magnesium, which is 2.37 volts. And then we're going to add that to our voltage for copper, which is 0.34 volts. And when we add those together, we end up with 271 volts. Okay, so this is my E cell, my 271 electron volts. Okay, so the next thing that we need to think about is write the half reaction that takes place at the anode. So what takes place at the anode, oxidation or reduction? What's going to happen at the anode? So does anode stand for oxidation or for reduction? Emily Kurlikowski, do you remember?
What was the question?
Yeah, what takes place at the anode, oxidation or reduction?
Oxidation.
Yeah, if we remember our catchy little song, right? We start at the anode, electrons are lost there. So losing electrons is oxidation. So the half reaction that would occur at the anode is going to be the thing that is oxidized. So Emily, which thing gets oxidized? Is it the magnesium or is it the copper? Which thing got oxidized?
The magnesium.
Yeah, the magnesium got oxidized. So how'd you know it was magnesium that got oxidized? You're absolutely right.
Because it gained 2 electrons.
Did it gain 2 electrons? Because we're going to go
I
from
don't know.
magnesium solid to magnesium 2 plus. So our charge just increased from 0 to positive 2. So do we get more positive or more negative?
More positive, I meant ions.
Yeah, we got more positive. So that means that our magnesium got oxidized. It lost 2 electrons because we can see that the electrons are on the product side of things. Okay, so remember that anode equals oxidation. Okay, and then write the half reaction that takes place at the cathode. Lisa, what is going to be the reaction that takes place at the cathode? What happens at the cathode? Are electrons
gain
oxidized or
electrons?
Yep, gain electrons. So what does that mean? Oxidation or reduction?
Reduction.
Reduction, right? And if we remember our little phrase, red cat, right? Reduction at the cathode. So what is the half reaction that we're going to see here, Lisa?
You're going to see the Cu2 plus the 2 electrons equals copper.
Yes. So we're going to have our copper ions reduced to copper solid. Okay. All right. So it says after the reaction has been allowed to take place, what will happen at the anode? So if we are doing oxidation, what's going to happen to the anode? Is it going to gain mass or lose mass? So we said the anode is our magnesium solid. So our solid piece of magnesium metal is going to lose electrons to become magnesium ions that are dissolved in water. So at the anode, is our magnesium metal going to gain mass or is it going to lose mass? Emily Augustine, what do you think?
Is it gonna lose mass?
Yeah, why is it going to lose mass? You're absolutely right.
Because it's turning from a solid to an aqueous solution.
Exactly. So that solid electrode that's over there, we're going to actually lose some of those solid magnesium, and it's going to turn into a dissolved substance in the solution. So absolutely. So the anode is going to lose mass. So it loses mass as magnesium solid gets converted to aqueous ions. Okay. After the reaction has been allowed to take place, what do you think is happening to the mass of the cathode? Annika, what do you think?
It'll gain mass because it's being turned into a solid.
Absolutely. So at the cathode is going to gain mass as copper ions are converted into solid copper. So we're going to actually see the copper electrode gaining mass. We're going to see that adding mass to it. Okay. So we're going to do some labeling of our picture here in a minute, but let's actually watch this happen. So we're going to go back to our lab for just a moment. Okay, so we have this lab situated right here. And what we can see is this is running. Look at the voltage compared to the voltage that we calculated. We said it was 2.71. This is 2.72. It's just a little difference of rounding. Right is always the anode? No. Right is not always the anode. We have to actually think about the half reactions that are there and what's taking place. The anode is always where the oxidation occurs, and that can be set up on the left or the right. Okay. In this particular demonstration that we're looking at, we can see that we put the copper over here on the left, and we put the magnesium on the right. In theory, you could set up a cell that would be the other way around. So if we take a look, if I reset this, I'm going to do a full reset. What I want you to look at, again, on the left side, we're going to copper, and we'll put magnesium. What I want you to take a look at is when I hit start, so do you see that these are full pieces of metal? So here's our copper. And what we said was the copper is going to gain mass, and our magnesium is going to lose mass. So here's magnesium over here. Watch when we turn this on. You guys see that the magnesium kind of shriveled a little bit, and the copper has actually gained some mass. You can see some additional on there. So if we look at the molecular scale, here's what's going on in the magnesium side of things. So electrons are being lost, and we can actually see magnesium atoms being converted to magnesium ions. So let's watch that again. So the electrons get lost, and we've converted that magnesium atom into a magnesium 2+ ion. And so we're losing mass at the magnesium side. And then if we look here, electrons are going to combine with copper ions, forming copper solid, and that's going to end up being plated on the surface, and the copper is going to get heavier. Okay. So what we're going to do is we're going to label what's going on. And so here is my setup, my solutions. So the first thing we need to do, it says label the magnesium electron. So if we want to set it up to look like what we have in our experiment, so we would have our magnesium over here. So this is our magnesium electrode, Mg. This over here would be my copper electrode. Okay, so we're taking care of that. We have our solution of magnesium ions, okay, and of copper ions in each of these solutions. Okay. It says we need to label the anode and the cathode, so we decided that the anode is where oxidation takes place, so the anode is going to be magnesium. Means this other side is our cathode. The salt bridge we have is right here, so this U-tube looking thing, the original U-tube is our salt bridge. Okay. And then voltage, so this is our voltmeter, which we calculated is 2.71. And then it says, draw the direction that the electrons are going to travel. So remember our little song, we start at the anode, electrons are lost there, they flow through the wire and through the load on fire. They go to the cathode and reduce the cations. So our electrons are going to go from the anode this way. Okay. So our electrons are lost at the anode, they go through the voltmeter, and then they return to the cathode. Then it says, write the ions that exist in the salt bridge. Okay. So what's going to happen here is at the cathode, this is reduction, right? This is oxidation. Okay. So what's going to happen with this is that at the anode, right, we're going to be oxidizing. So magnesium is going to become magnesium 2+ over here. So we're going to start to get a buildup of positive ions. To balance out those positive ions that are getting built up over here, what's going to happen is in the salt bridge, we're going to have sodium nitrate, okay? So we're going to have NO3 ions go this way. And the purpose of these NO3 ions are to cancel out the positive charge from these positive magnesium ions that are being made, right? Because what's happening here, the half reaction that's happening over here, is we have magnesium solid turning into magnesium 2+ plus 2 electrons, right? So we get these positive ions here. So to balance out that charge and to keep an equilibrium of charge, we're going to get negative anions flowing this way. And then our salt is made of NaNO3. We could use other salts, but this is the one we're using because they stay aqueous. The opposite is true in that these copper ions, these positive copper ions, are going to get converted to copper solid. And so what we're going to end up with is a deficit of positive over here. So the positive sodium ions are going to go over here to the cathode side of things to balance out that charge. And then the arrows to show which direction. The Na, so the positive ions in the salt bridge are going to go to the cathode, and the negative ions in our salt bridge are going to go towards the anode. Okay. Any questions about what to label, how to label, what to do there? Okay.
So the anode will always receive the negative end of the salt, right? To balance out the loss of electrons. And the cathode will always receive the positive end to balance out the extra negative electrons, right?
Yes, that's exactly what's going to happen, Ami. Yep. Yep. Any questions with that? So no matter what, like if we had arranged the anode over here and the cathode over here, the electrons would have flown the other way. But the electrons always go from the anode to the cathode. We figure out which one is the anode and which one is the cathode by looking at the half reactions, right? And making sure that we're setting this up so that we end up with an overall positive E naught, which is our electrochemical cell potential. We're always looking for positive. Yeah. This has to do with lithium-ion batteries and batteries in general. Okay. Any questions on this? Should we try a little bit more practice together? Does that help to see it this way? So back to our virtual lab here, because I didn't show you what's going on at the salt bridge. So you can actually see this on the salt bridge as well. And if you want to play around with this, you can put together all sorts of different combinations to see how different electrodes change. But if we look at the molecular level, we can see that our negative nitrate ions are flowing towards our anode, and our positive sodium ions are floating toward our cathode. So that's what's going on in the salt bridge. Any other questions on that, guys? Okay, let's try some more. So here, without a diagram, so we'll go back. Okay. So example 2, it says, given these two half reactions, write a thermodynamically favored balanced overall reaction. So what are we going to do to get an overall balanced reaction? What would we need to do? What are we going to flip? Olivia, what do you think?
Do we have to flip both of them first?
Did you flip both of them? So what would happen if we flip both of them? So right now they're both reduction. If we flip both of them, what would they both be then?
Then they'd both be oxidization.
Yeah. So if we flip, I love that you asked that question, because yeah, if we flip both of them, they'd both be oxidation. So yes, that would give us a super positive E cell value, but it wouldn't work because we have to have one oxidized and one reduced in order for this to work. So that means we can only flip one of them. So which one of them would give us the greatest positive charge that we could get? Which one would we want to flip, Olivia?
You'd want to flip the Na.
We want to flip the Na, right? So if we look, Na has the larger negative value, so this is the one we're going to want to flip. Okay. So that would become Na solid, giving us Na plus, and then negative electron. Okay. So that's what would happen when we flipped it around. And the E naught value of the flipped equation would be positive 2.71. So what would be the thermodynamically favored balanced overall equation for this? What would we end up with for our overall balanced equation? Ethan, what would we get?
The concentration of Na plus E.
Okay. And so what would be the balanced equation?
The concentration of
Not
Na.
concentration. So we're not,
Oh,
we're
yeah,
not,
yeah.
we're not writing like an equilibrium expression. We're writing a balanced chemical equation. So we had to flip this one around. So Olivia told her we're flipping this equation, but we're leaving this one alone. So what would we end up with?
The Mg
Okay,
plus,
Mg, what
plus
is the charge? 2 plus?
2E
Okay.
plus
So,
Na, right?
mhm.
To Mg. I can't see the rest of that.
Yep.
And then Na E.
So Mg solid.
And then Na.
Okay. Plus Na plus.
Yeah.
And then that would be 1 electron. Do those electrons cancel?
Not all the way.
Not all the way, right? Because we have 2 of them over here and only 1 of them over here. So what are we going to have to do to make sure that this equation, we'd have the same amount of electrons on both sides? What would we need to do?
We got to add an electron onto the right-hand side.
Okay, so how can we do that? We could multiply this entire thing by 2.
Yeah.
Okay, so when we do that, that's going to be 2 Na solid and 2 Na plus will give us 2 electrons. So now our electrons cancel and they don't need to be a part of our overall net equation because they've canceled out. So those would be gone and those would be gone. So our overall equation would be magnesium 2 plus aqueous plus 2 Na solid yields for us magnesium solid plus 2 Na plus. Okay, so that would be our overall equation for our thermodynamically favored reaction. Okay. Then it says calculate the voltage for this cell. So what would the voltage be? Emily, what do you mean by are we able to flip either one? We could have flipped Mg, but the problem is it wouldn't leave us with an overall positive E cell. So if we had flipped this one, we would have gotten a positive 2.37, but when we added it to the negative 2.71, the E cell total would still be negative. And we need it to be thermodynamically favorable. We need the overall E cell to be positive. So yes, so you always flip the larger one. The larger negative one, right? Yeah, so you're always going to flip the larger one. You're trying to look for what's going to give you the largest possible positive value. Does that make sense? Yeah. So when they're both negative, you always flip the larger one. You can end up a situation where they're both positive. Then you would want to flip the smaller of the two, okay? But what you're looking to do, if they're both negative, you're going to be flipping the larger of the two. But you're going to be flipping the one that's going to, when you add them together, allow you to have an overall positive E cell. So then if we take a look, once we flip this, it's going to be negative 2.37 plus positive 2.71, and that will give us our overall E cell of 0.34. And that's EV, which is electron volts. So now it says, write the reaction that takes place at the anode. So again, the first thing we need to think about is what takes place at the anode. Is that where oxidation occurs or reduction? So Pamela, at the anode, is that oxidation or reduction?
Oxidation.
Yep, so anode is oxidation. So which of my half reactions, this one or this one, represents oxidation?
2Na.
The 2Na solid is going to go to 2Na plus 2 electrons. Okay, good. And then what is going to be the half reaction that takes place at the cathode? So which one would that be at the cathode? Drew, what would it be the one that takes place at the cathode?
Mg.
So is that an oxidation or a reduction?
Reduction.
Reduction. So we've got Mg2 plus aqueous plus 2 electrons. Right? Adding 2 electrons to it, it's gaining it. That means it's reduction. Is going to give us solid magnesium. Okay. So what will happen to the anode? So what's going to happen to the anode? Is it going to increase in mass or decrease in mass? Connor, what do you think?
I'm sorry, what was the question?
Yeah, so the anode, is it going to increase in mass or decrease in mass?
Increase because you're adding electrons.
So if we take a look, the anode is where oxidation takes place, right? Oxidation means we're taking the solid sodium and we're converting it into sodium ions, which are aqueous. So is that piece of sodium metal going to gain mass or lose mass?
Oh no, it's gonna lose mass.
It's going to lose mass. Why?
Because you're going from solid to liquid. Wait,
Yes,
no, not
solid
liquid.
to aqueous, yeah.
Yeah.
So it's going from solid metal to dissolved ions, okay? The anode, and this will always be true, will lose mass as solid Na is converted to aqueous sodium ions. Okay. After the reaction has been allowed to take place, what will happen to the cathode? So what do we think is going to happen at the cathode? Let's see. Sandra, what do you think is going to happen at the cathode? Excellent. So the cathode, that was a great explanation, Sandra. So Sandra said that the cathode will increase in mass. As aqueous ions are converted to solid. Those aqueous magnesium ions are converted to solid. Good. take a look at the next one. I think we're starting to get the hang of it. Sounds like it. All right, it says write the thermodynamically favored balanced equation for the overall reaction. So we have these two half reactions for water and iron, and it says write the overall thermodynamically favored balanced reaction. So what would be our overall balanced reaction for this one? Annika, what do you think we would get?
First, you would have to flip the Fe equation, right?
Okay, yep, why?
Because otherwise your E is going to be negative.
Yep, so we'll flip this guy around. So Fe solid gives us Fe 2 plus 2 E minus. So what are we going to get for our balanced equation?
You would get 2H3O plus the solid Fe would turn into H2 and H2O plus the Fe2 plus ion.
Yeah, perfect. Okay, we didn't have to multiply anything because we have the same amount of electrons, right? 2 electrons and 2 electrons, so they would cancel. All right, so what would be the overall voltage for this particular cell? What would we get? Ethan, what would be the overall voltage of the cell?
For this one, it will be we're looking for the voltage, right?
Yep, what would we do? What numbers are we adding together?
It's gonna be the hydrogens, right?
So what do we have for the voltage for that one?
I can't see it. Is it 1?
Nope, that would be 0.00.
Okay, so 0. And
Uh-huh.
then we gotta add the voltage for the other one.
So we
But-
flip that around. It was negative 0.45. So what is it going to be?
0.45.
So positive 0.45. So 0 plus 0.45 is 0.45. Okay. What is going to be the half reaction that takes place at the anode? Notice that these questions are the same, like over and over again. Once you kind of get the hang of it, they're all the same. So Drew, what is going to be the half reaction at the anode?
Fe solid. And then that converts to Fe2 plus aqueous plus 2 E minus.
Perfect. Why did you pick that one? What takes place at the anode?
That's the one that's losing electrons.
Yep, which is called oxidation. Good. So what is going to be the half reaction that takes place at the cathode then? Lisa?
At the cathode, it's reduction, so it would be 2H2O plus 2 electrons is equal to H2 plus H2O.
Perfect. Okay, good. What's going to happen at the anode in this particular case? So notice that this is liquid, and we're producing hydrogen gas and liquid water. Okay, so that's cathode and oxidation of anode. What's going to happen at the anode? Gain mass or lose mass? Pamela, what do you think?
It's gonna lose mass.
Okay. And then what's going to happen at the cathode? This is going to be a little bit different. What's going to happen at the cathode? Monica, what do you think? What are we producing at the cathode, Annika?
A gas and a liquid.
A gas and a liquid. So what do we think is going to happen there?
Would it lose mass?
So it's going to lose mass from the gas that's going to be given off, absolutely. And then what about the liquid water that we're making here? What do you think is going to happen to the volume of the liquid inside the container?
The volume will increase.
Yep, so we're going to get a slight increase in the volume of water that's in that container. So the volume is going to increase just slightly. And then H2 bubbles will be given off. And what do you think is going to happen to the pH of the solution? So here we have H3O ions, and we've converted that to H2 and water. So what do you think is going to happen to the pH of the solution? Let's see. Emily Gustin, what do you think is going to happen to the pH of the solution? Increase or decrease? Emily Gustin, are you there?
Yeah.
Yeah, what do you think is going to happen to the pH? So if we're converting H3O plus back to hydrogen gas and water, are we going to be more acidic or less acidic?
Less acidic.
Yep, so what's going to happen to the pH? Increase or decrease?
Increase.
Increase, good. pH will increase as the concentration of H3O plus decreases. Good. Oh, and that is way off the screen. I'm so sorry, guys. What's up, Bobby?
I have a question about the equation for the H3O. So there's 6 hydrogens and 2 oxygens. Where are the other what is it, like 2 hydrogens and other oxygen in the reactant? I mean the product side.
Product side? Oh,
Mhm.
where we have, yeah, it's not balanced. There should be a 2 here. Sorry. Yep, there definitely should be a 2 there. It's just missing. Now it'll be balanced because we'll have 2 plus 4, which is 6 hydrogens, 2 oxygens, 2 oxygens. Yeah, it was just missing the 2 there. Good catch. Thank you. Good. Are we feeling a little bit better about these? Understanding them, I hope? Yeah? All right. With the last few minutes, what I want to do is take a look at the questions that you guys asked about the homework. Okay. It looks like it was just general questions. So I'm hoping that by going through these, those of you who said, like, can we go over all of it? If this was helpful, you guys feel a little better prepared to do the other one? let's do some more practice. So what I want you guys to do as your homework for tonight is there are 1, 2, the number is off. So 1, 2, there should be 3, 4. So there's 4 practice problems left to do. They're all very, very, very similar to what we were just doing all together. Okay. So practice 2 starts here, ends here. So you're just going to finish by labeling this whole thing. But this one right here, let's look at number 5 for just a minute. The other ones are going to be really similar to what we just went over. So let's take a look at this one right here. It says, which combination will have the most thermodynamically favored reaction with the reduction reaction copper? Cu must be reduced. Support your answer with calculations. So when we're talking about which combination would be most thermodynamically favored, what do you think we're looking for? If we're looking for the most thermodynamically favored. In terms of voltage, what do you think we're looking for? If we want to find one that is most favored. Sandra, do you know? What do you think we're looking for if we're looking for the one that would be most favored? Yes, we're looking for the biggest positive possible voltage we can get, okay? So it's saying that the copper has to be the thing that's reduced. So looking here, we're keeping this reaction, we're keeping copper as reduced, right? And so that's copper 2 plus 2 E minus reduced to copper solid. And that is an E naught, so standard condition of 0.34 volts. So which one of these, right, are we going to put with it? And they have to be flipped because all of these are reduction potentials. So we're going to have to flip them. Which one would give us the most positive overall electrocell potential? Which one would we choose and why? Drew, what do you think? Which of those 3 would we choose? Would we choose nickel, manganese, or gold? Which one would you choose?
Manganese.
Manganese? Why manganese?
Because you're gonna flip it and oxidize it.
Yeah, we're going to flip it and oxidize it. So what's going to happen to this voltage here?
It's gonna switch to positive.
It's going to switch to positive. This is our biggest number, though. So why didn't you choose gold?
Because you'd have to flip copper and that would be less.
Yeah. So it's telling us we have to keep copper in this direction, so we have to keep copper reduced. So if we were to use the gold, we'd have to flip it, and then that would be a negative 1.5. So absolutely, this one is going to be the best, because when we flip that around to Mn solid, giving us Mn 2 plus 2 electrons. When we flip that around, the E cell value for that is going to be positive 1.19. And then when we add that together, that would give us, as Sandra said, the largest possible total. So 3, 2, 1, 4, 5, which would give us a positive 1.53 volts. Good. So we would choose manganese. The other ones are very similar to what we just did together in class. I hope this makes a lot more sense. Of course, now we finally kind of got these under our belt. We're going to learn a twist on the situation tomorrow. We're going to talk about if the conditions are non-standard. All right, friends, thank you so very much. I will see you tomorrow at 1 o'clock, please. The link will be posted in Classroom.